Today we will start looking at inference problems, inference about multivariate normal distribution. So specifically we have already introduced what is a multivariate normal distribution and what are the characterizing parameters of a multivariate normal distribution. So today we will address the problem of inference about the multivariate mean vector mu and the covariance matrix sigma. So we have actually the following setup that it's basically a random sampling from a multivariate normal distribution. So random sampling from multivariate normal distribution. So suppose we have a population multivariate normal population NP mu sigma. So what we have here is this mu to be giving the mean vector and sigma to be the covariance matrix. We assume that sigma is positive definite. Now the elements in mu, this mu vector is unknown and so is the sigma matrix. So what we do is we take random samples from this multivariate population and then try to build up the inference procedure concerning the unknown mean vector mu and the unknown covariance matrix sigma. So what we do is we take a random sample x1, x2, xn be a random sample from this multivariate normal population, and then using this random sample x1, x2, xn, the random sample of size n, we will build the inference procedure about the mean vector mu and the covariance matrix sigma. Now given this random sample, the joint PDF of x1, x2, xn, remember that it is a random sample and hence this x1, x2, xn are independent. So that the joint distribution, the joint PDF of x1, x2, xn is given by the following, that I equal to 1 to n, then the PDF of the respective components x1, x2, xn. So that this is f xi xi. So that this is equal to I equal to 1 to n 2 pi to the power minus p by 2 determinant of sigma to the power minus half, then exponent minus half xi minus mu transpose sigma inverse xi minus mu. Right. So this is what is the joint PDF. So this can be compactly written as 2 pi to the power minus np by 2 determinant of sigma to the power minus n by 2, then exponent minus half summation I equal to 1 to n xi minus mu transpose sigma inverse xi minus mu. So the first thing about this random sample x1, x2, xn from the multivariate normal distribution, the first question that we are going to answer is that what is the sufficient statistic that is based on this random sample x1, x2, xn, right. So we move on to the sufficiency. So we will be deriving sufficient statistic under various possibilities. So let us consider the first case, case 1, which is the most general case, mu and sigma are unknown. So we have both the two parameters characterizing this multivariate normal population, the mu vector and the covariance matrix sigma, both of them are unknown. Right. Now let us consider this particular term which is present in the exponent. This is the term which is present in the exponent. Let us see how we can manipulate this particular term. This is summation I equal to 1 to n xi minus mu transpose sigma inverse xi minus mu. So we introduce an x bar term Now note that this derivation of sufficient statistic for the multivariate normal population goes along exactly in the same line as to what we usually do when we have an univariate normal population. So we introduce this x bar vector, which is the sample mean vector, in this following way: sigma inverse xi minus x bar, the same adjustment in the second term as well. So this, now we will split it into two terms. This is one term here and this is a second term here, and then take sigma inverse multiplication term by term. So the first term would be xi minus x bar transpose sigma inverse xi minus x bar xi minus x bar, and then this term multiplied by sigma inverse into this particular term. Now that is a term which is independent of I, and hence we will have n times x bar minus mu transpose sigma inverse x bar minus mu, and then the cross product term of this term multiplied by this and this second term out here. And the two terms would be similar, the two cross product terms, and what we will be having is the following, that it is summation I equal to 1 to n xi minus x bar transpose sigma inverse x bar minus mu. Now this is, if we look at the two factor here, it is basically coming from the cross product, because we will be having two terms which are similar, just differing by transpose, and the two terms are same. Now what is going to happen with this particular term is the following. So let me put this as equation number 1. Now if we look at this expression here, what is that going to give us? Note that this summation I equal to 1 to n xi minus x bar transpose sigma inverse x bar minus mu. Now this term, now this part here is independent of I, and hence it can stay outside the summation. So what we will be having is summation I equal to 1 to n xi minus x bar transpose, and then that is post multiplied by this sigma inverse x bar minus mu, which is independent of I. Now what is going to happen when we look at the summation here? It is going to give us 0, because it is the deviation from this mean vector mu x bar vector, sample mean, and hence this is going to give us n times x bar transpose minus n times x bar transpose. So this is n times x bar transpose minus this x bar transpose times sigma inverse x bar minus mu, and that is equal to 0. So this cross product term in equation number 1, this specifically, so this term is going to vanish because this is equal to 0. So we will have thus, so this will imply that this summation I equal to 1 to n xi minus mu transpose sigma inverse xi minus mu, this term is equal to summation I equal to 1 to n xi minus x bar transpose sigma inverse xi minus this x bar, right. So this is basically that term out here. What we have this as the first term, and the second term remains as it is, and the third term vanishes. So we will have that n times x bar minus mu transpose sigma inverse x bar minus mu, right. Now this is a scalar quantity, and hence we can write this as trace of this term here, summation I equal to 1 to n xi vector minus x bar vector transpose sigma inverse into xi vector minus this x bar vector, right. Leave the second term as it is, n times x bar minus mu transpose sigma inverse x bar minus this mu, right. Now, trace of a plus b is trace a plus trace b, and hence we can take the trace inside. So, we can write this as a summation I equal to 1 to n trace of this term which is inside the summation. So, this is xi vector minus this x bar vector transpose sigma inverse xi minus this x bar vector. Leave the second term as it is. So, x bar minus mu vector transpose sigma inverse x bar vector minus this mu vector, right. Now, here we have trace of this particular quantity which is a scalar quantity. So, what we will do is we will use the result that trace of AB equal to trace of BA, where we consider this to be A first term and this to be second term. So, trace of A B would be trace of B A. So, this would be given by summation I equal to 1 to n trace of sigma inverse xi vector minus x bar vector, that multiplied by this particular vector out here. So, that is xi minus this x bar transpose, second term is left untouched, sigma inverse x bar minus this mu, right. Now, this sigma inverse is something which is actually independent of this I index out here. We will once again make use of the fact that trace of A plus B is trace of A plus trace of B, and hence we can take this trace outside also. So, we will write this as trace of sigma inverse is independent of this I index, and hence it can be taken outside the summation. So, what we have is trace of sigma inverse I equal to 1 to n xi vector minus x bar vector, that multiplied by xi vector minus this x bar vector transpose, that plus the second term carried forward as it is. So, this is x bar vector transpose sigma inverse x bar minus this mu vector, right. Now, what is this particular term? If we look at this particular term here carefully, it is nothing but a constant multiplier of the sample variance covariance matrix. So, we can write that as trace of sigma inverse times n minus 1 times S, that plus n times x bar vector minus this mu vector transpose sigma inverse x bar minus this mu vector, where we have used the notation that n minus 1 times S is the sample variance covariance matrix with a divisor n minus 1. So, that is equal to summation I equal to 1 to n xi vector minus this x bar vector into xi vector minus x bar vector its transpose, right. So, this term here, which was actually in the exponent of the joint PDF, this was actually, if we look at this term here. So, the term which we have simplified and reduced it into that form is nothing but here sitting in the exponent. So, we will go to that term there. So, we have that term as trace of sigma inverse n minus 1 times S plus n times x bar minus mu transpose sigma inverse x bar minus mu. So, we will use this term. So, this would imply that the joint PDF of x1, x2, xn, the random sample of size n from that multivariate normal distribution with mean vector mu and covariance matrix sigma, is given by the following, that it is 2 pi to the power minus np by 2 determinant of sigma to the power minus n by 2, and then the exponent term is what we have done simplification on. So, that is n minus 1 by 2 trace of sigma inverse S, S is that matrix what we have defined in the last slide. So, this minus n by 2 x bar vector minus this mu vector transpose sigma inverse x bar minus mu. Now, when the joint PDF of x1, x2, xn is written in this particular form, it is easy now to use the Neyman-Fisher factorization theorem in order to derive what is the set of sufficient statistic when we have both the parameters mu vector and the covariance matrix sigma to be unknown, right. Now, this is written in this form. I'll say what these are basically. So, I am writing it in this way, f x1, x2, xn. Now, this let me first complete this and then I will explain what these quantities are. Now, I am factorizing this particular joint PDF of x1, x2, xn in the form that the first term is a function only of x1, x2, xn. It does not include any parameter in this particular distribution. The parameters are mu vector and the covariance matrix sigma, and the second part is written as a function. It is a function of mu and sigma, and it is a function of x1, x2, xn, the random sample, only through x bar and s, right. So, this is a function which depends on mu sigma x1, x2, xn only through x bar and s, right. So, what are these functions from the joint PDF that we have written here? So, that let me put a number here, equation number 2. So, we will have this particular quantity here what we have defined. So, this f x1, x2, xn, we will have to look for the terms in 2 which depend on x1, x2, xn only. So, it cannot involve any mu, it cannot involve any element of sigma. So, this, as we see, that it is a constant function which is 2 pi to the power minus np by 2. All other terms which are present here depends on mu and sigma. So, it cannot be separated from there. And the second function that we have introduced, g mu sigma x bar and s, is basically the rest, which is determinant of sigma to the power minus n by 2 and then exponent minus n minus 1 by 2 trace of sigma inverse s minus n by 2 x bar minus mu transpose sigma inverse x bar minus this mu. We close the bracket here, right. So, this is a term which depends on sigma. Sigma is here, and so it is here. It depends on mu, mu is present here and mu is present here, and it depends on x1, x2, xn, the random sample, only through the two statistic, which is x bar vector, the sample mean vector, and s, which is the sample variance covariance matrix. And hence, if we use this particular factorization, it is in the form of the Neyman-Fisher factorization, and hence by Neyman-Fisher factorization theorem, by Neyman-Fisher factorization, we have x bar, the random vector, x bar, the sample mean random variable vector, and s is jointly sufficient for the unknown mu and sigma. So, this basically is the set of jointly sufficient statistic for the unknown parameters, the mean vector mu and the covariance matrix sigma. So, if this is a set of sufficient statistic, as in any other statistical inference problem, instead of carrying x1, x2, xn, the entire set of random samples, we can carry this x bar vector and this S, the sample variance covariance matrix, for all the inference procedure concerning this mu vector and covariance matrix sigma. So, this gives us the desired compression of the data without loss of information. So, this contains all the information that is present in x1, x2, xn about the parameter vector mu and the matrix sigma, the population variance covariance matrix. So, this will be the jointly sufficient statistic if we have both these two parameters, both these two set of parameters rather, to be unknown. Now, we move on to the second possibility where sigma is known to us. So, we look at case 2. Sigma is known and this mu vector is unknown. So, it is a theoretical possibility actually, or for all practical purposes what we usually have is both the mean vector mu and the covariance matrix sigma to be unknown, but it is a theoretical possibility that we have sigma matrix to be known and the mu vector to be unknown. Then if this is the only parameter set present in this population, we will try to compress the data so that it would contain every information that is present in the data about this vector mu, right. Now, how are we going to do that? Now, note that we had this as a joint PDF of x1, x2, xn, right. So, we will use this particular form itself and then use the Neyman-Fisher factorization in order to get to the sufficient statistic. And what is that? The joint PDF of x1, x2, xn is once again what is going to be used in order to find the sufficient statistic. So, this as we have seen is 2 pi to the power minus np by 2, determinant of sigma to the power minus n by 2, e to the power minus n minus 1 by 2, trace of sigma inverse s, this minus n by 2 x bar minus mu transpose sigma inverse x bar minus this mu, right. Now, if this is this, we write it as another function f1 x1 x2 xn. So, we are trying to reduce it to the form of the Neyman-Fisher factorization. Now, the only unknown parameter in this case 2 is the mean vector. So, we are trying to find out what is that particular function which depends on mu and also depends on x1 x2 xn through some statistic. Now, we will see that it can be reduced into this particular form where the first function f x1 x2 xn is a function of x1 x2 xn. So, that is basically a known function when we have x1 x2 xn to be given. So, this now takes the form that it is 2 pi to the power minus np by 2. Now, note that sigma is now known to us. We have assumed in case 2 that sigma is known and hence this determinant of sigma is also known to us. So, this also is a function which is known, and if we look at in the exponent, the first term is n minus 1 by 2 trace of sigma inverse s. Now, sigma is known to us and so will be sigma inverse, and S is a matrix which is based on x1 x2 xn only. So, this also thus would be absorbed in the first function. So, this is e to the power minus n by 2 trace of sigma inverse S, right. So, this entire function here thus is known to us if x1 x2 xn is known to us, and this g mu sigma g mu vector x bar. So, this is thus the rest of it, which is e to the power minus n by 2 x bar minus this mu transpose sigma inverse x bar vector minus this mu vector. So, what is the characteristics of this particular function, the second function? It depends on mu, well, that is clear, and it depends on x1 x2 xn through this x bar vector. Note that once again sigma is known to us, so and so will be sigma inverse, right. So, this is a function which depends on the unknown parameter vector mu, and its dependence on x1 x2 xn now is compressed through, it is compressed in terms of this vector x bar, right. So, this in this particular form, the factorization once again we will be using the Neyman-Fisher factorization. By Neyman-Fisher factorization, the Neyman-Fisher factorization theorem will tell us that this x bar vector, random variable, so this x bar vector is now sufficient for the unknown mean vector, right. So, if both mu and sigma are unknown, then x bar and s is jointly sufficient for mu and sigma. If sigma, the population variance covariance matrix, is known, then x bar is sufficient for mu. Now, we look at the third possibility, which once again is a theoretical possibility. Suppose in the third possibility mu is known, say equal to mu naught vector, and the covariance matrix sigma is unknown. So, if this is the setup, then we will try to find out what is the sufficient statistic corresponding to the unknown, this sigma matrix, right. Now, the joint PDF, we do not need to look at the form of the joint PDF that we had derived. We will take the original form. The joint PDF of x1 x2 xn is 2 pi to the power minus np by 2, determinant of sigma to the power minus n by 2, then this e to the power minus half summation I equal to 1 to n xi minus mu naught, because we have assumed that the mu vector, the mean vector mu is known to us, and that is equal to mu naught. So, we plug in this particular value out here, sigma inverse transpose xi minus this mu naught vector, right. Now, if we have this particular form, we are trying to derive, remember, we are trying to derive the sufficient statistic under the condition that mu is equal to mu naught is known to us and sigma is unknown. So, we will once again have to use the Neyman-Fisher factorization theorem. So, let us write these terms as it is, and then we will write this exponent term as, now note that this particular term is a scalar quantity, and hence we can write trace of that particular quantity. So, it is half trace of summation I equal to 1 to n xi minus mu naught transpose sigma inverse xi minus mu naught. So, once again we will use this trace of a plus b is trace a plus trace b, and trace of ab equal to trace of ba. So, using the two trace results, what we can have is this quantity exponent. So, we will take first the trace inside, and then we will consider this to be one term, this to be one term, and along with sigma inverse this to be the second term, and then flip these two terms. So, trace of a b will be equal to trace of b a. So, that this thus will reduce to half trace of sigma inverse times summation I equal to 1 to n xi minus mu naught into xi minus mu naught this transpose, right. So, we have taken this trace sigma inverse outside. So, this once again we will write it as a function, say f2 x1 x2 xn. Our objective is to use the Neyman-Fisher factorization theorem, and this, the unknown quantity is sigma now. So, we will have to write it in terms of sigma and some statistic here. Let us write this as some t. We will have to define what is t, where the first function f2 x1 x2 xn now would be a function of x1 x2 xn and only known quantities. What is that? If we look at this term, only this is the term which satisfies that particular criterion. So, this is 2 pi to the power minus np by 2, and this g sigma t is basically determinant of sigma to the power minus n by 2 and e to the power minus half trace of sigma inverse, I denote this entire quantity what we have here as this T matrix. Now, that T matrix is a function of x1, x2, xn. So, this is T of x1, x2, xn only, right, because mu naught is known to us. So, that is a known quantity, and this T x1, x2, xn is nothing but this particular matrix, which is summation I equal to 1 to n xi vector minus this mu naught vector, that multiplied by this xi vector minus mu naught vector, its transpose. So, see what we have obtained. We have obtained the following, that this, the second factor is a function of the parameter matrix sigma. Sigma is appearing here, and so it is present here, and a term and a quantity which we have denoted by T x1, x2, xn. It depends on x1, x2, xn through this particular matrix. So, that would imply, by Neyman-Fisher factorization, once again, by Neyman-Fisher factorization, this T x1, x2, xn, which is summation I equal to 1 to n xi minus mu naught xi minus mu naught transpose, is sufficient for the unknown parameter matrix, which is sigma matrix, right. So, this is all the three possible cases when we talk about sufficiency that is going to be derived on the basis of the random sample x1, x2, xn. The first case, we had seen that that is the most general case, that is the most practical case actually, that both the mean vector mu and the covariance matrix sigma are unknown to us, and in such a situation x bar vector and the sample variance covariance matrix S is jointly sufficient for mu and sigma. In the second case, we had assumed that sigma is known to us, mu is unknown. So, if that is the situation, then the x bar vector is going to be sufficient for the unknown mean vector mu, and in the third case we had the mean vector mu to be known to us, say equal to mu naught, and in such a situation this matrix T, what we have, this statistic actually is sufficient for the sigma matrix, right. That is all about this sufficiency possibilities when we are considering a multivariate normal distribution. Now, a second point of interest that one usually is interested in is what is this unbiased estimator corresponding to these unknown quantities. So, let us answer this question. Unbiased estimators. Now, we have this mu and sigma both unknown. So, if both this mean vector mu and the covariance matrix sigma are unknown, so this is corresponding to the case 1 what we had considered for sufficient statistic. So, in such a situation we have already derived for a general case of a random sampling from a multivariate distribution, not necessarily a multivariate normal distribution, that if we have this x bar vector is the sample mean random vector. So, that is this I equal to 1 to n. From here we had seen earlier that expectation of this x bar vector is the population mean vector mu. So, this would imply that x bar vector is an unbiased estimator of the population mean vector, which is mu, right. Now, what about the sigma matrix? We have once again in the earlier lectures had proved that if we consider S to be equal to 1 upon n summation 1 upon n minus 1 summation I equal to 1 to n x I minus x bar into xi minus x bar transpose. So, this is a sample variance covariance matrix with a divisor n minus 1. Then we have already proved this result, that expectation of this S matrix is nothing but this sigma matrix, right. That is for a general case that we had proved, not necessarily for a multivariate normal distribution. The result still holds true if we have the underlying distribution to be a multivariate normal distribution. So, this would imply that S is an unbiased estimator of the covariance matrix, which is sigma, right. So, S is going to be an unbiased estimator of sigma and x bar is going to be an unbiased estimator for mu. So, we will have the two. If on the other hand we consider S the sample variance covariance matrix with a divisor n, then that is definitely not going to remain an unbiased estimator. So, that is going to be a biased estimator for the small sample. However, for the large sample it is going to be unbiased in the limit, right. So, this x bar is an unbiased estimator of the unknown mean vector mu, and S with a divisor n minus 1 is an unbiased estimator of sigma. On the other hand, if we have defined Sn to be 1 upon n of the same quantity as what we had considered, this xi, this is what I just referred to, that this quantity is biased estimator. However, this Sn is unbiased in the limit. So, these are the two unbiased estimator for the most general case that mu and sigma are unknown. The unbiased estimators in the other two situations where say sigma matrix is known to us or mu vector is known to us can similarly be derived, right. Now, let us move on to another important estimation procedure, which is the maximum likelihood estimator. Maximum likelihood estimator. So, we will be deriving the MLEs corresponding to this unknown quantities mu and sigma. We take the most general case where mu and sigma are unknown. The other cases of mu being known or sigma being known can be tackled in a similar way. So, suppose mu and sigma are unknown, we have still this x1, x2, xn random sample from that population np mu sigma. Then we will look at the likelihood function So, the likelihood function is L mu sigma given the observations x1, x2, xn, and that is nothing but the joint PDF actually looked upon as a function of mu and sigma given x1, x2, xn, and in order to find out the maximum likelihood estimators, we will try to see what mu and sigma basically maximizes this particular likelihood function. So, as we had seen earlier, the joint PDF, which we are now taking as the likelihood function, that is given by the following: 2 pi to the power minus n by 2 determinant of sigma to the power minus n by 2 and e to the power minus n minus 1 by 2 trace of sigma inverse S matrix, this minus n by 2 x bar minus mu vector transpose sigma inverse x bar minus this mu vector, right. So, this is now the likelihood function of mu and sigma given x1, x2, xn. Now, we note the following, that for a fixed sigma, positive definite, we will have the quantity which is here. Now, we are at the first step fixed this sigma to any particular matrix, any positive definite matrix, and then we will try to see what is the value of mu which would maximize this particular likelihood with respect to that particular mu vector. Now, sigma is positive definite. I will just extend this particular bracket little bit. Sigma is positive definite. Sigma inverse is also positive definite. So, for that fixed sigma positive definite matrix, sigma inverse is also positive definite. So, what we will be having is for that fixed sigma, x bar minus mu transpose sigma inverse x bar minus mu, this would be greater than or equal to 0. Why? Because sigma inverse is positive definite, actually that would be greater than 0 if we look at that. So, this is greater than or equal to 0. So, and 0 if x bar is equal to mu only, because sigma is positive definite. So, this sigma inverse being positive definite will imply that this quadratic form will be equal to 0 only if we have x bar to be equal to mu, that is this vector that we have taken here is just a null vector. So, this would be 0 if we have x bar to be equal to 0. Now, let me give an equation number star here, star 1 say. Now, for this fixed sigma, if we have this quantity, we can say that thus for a fixed sigma positive definite, star 1 is maximum with respect to this mean vector mu if we have, now note that in this likelihood function here mu is present only in the exponent. So, if we are trying to maximize the likelihood function star 1 with respect to mu for a fixed value of the sigma matrix, then this is going to be, this likelihood function is going to be maximized if the exponent is maximized. Now, in the exponent also you will see that this is a quantity which does not depend on mu, and hence if we are trying to maximize the exponent with respect to mu, then it is maximization corresponding to this particular part of the exponent. So, this for a fixed sigma star 1 is maximum with respect to mu if e to the power minus n by 2 x bar minus mu transpose sigma inverse x bar minus mu is maximum, right. So, we will be looking at what is the value of that mu which would maximize this particular quantity. Now, thus if we look at this exponent here, this exponent is going to be maximized if this part, what is sitting in the negative part of this exponent, is minimized, right. That is, if this x bar minus mu transpose sigma inverse x bar minus mu is, I am sorry, this is if that is minimum, if this part is. So, we are trying to find out what is that value of mu which would maximize this particular quantity, and that is equivalent to finding what is that value of mu which actually would minimize this particular quantity, because it has got a negative sign out here. And what is the value of mu that would minimize this particular quantity? We have seen that for the fixed sigma, this quantity is greater than or equal to 0, right. So, this quantity here is going to be minimized if we choose mu to be x bar. So, x bar vector is the one that is going to minimize this particular quantity, and hence that is what is going to maximize this exponent part here, and that would maximize the likelihood. So, that what we can thus say is that this would imply that this mu hat equal to x bar would maximize this star 1 likelihood with respect to this mean vector mu for a fixed sigma matrix. However, we see that this maximizing value of mu does not depend on the particular level of sigma where we have fixed, and hence this mu hat equal to x bar is going to maximize the likelihood with respect to mu for every possible values of sigma. So, that this would imply that the maximum likelihood estimator of mu is mu hat MLE is equal to the sample mean vector x bar, which was also incidentally the unbiased estimator, right. So, we have got this to be the maximum likelihood estimator of the mean vector mu. Let us now try to see what is the maximum likelihood estimator of sigma. In order to derive that, let us now look at the likelihood function at mu equal to x bar. So, the likelihood function at mu equal to x bar is, let us denote that by this as mu hat sigma x1 x2 xn, so that it is equal to 2 pi to the power minus np by 2 determinant of sigma to the power minus n by 2, and then we have in the exponent. Now, what would that look like? Let us look at the likelihood function. So, this is the likelihood function star 1, where we are looking at the likelihood function at the maximum likelihood point mu hat equal to x bar. So, here this x bar and mu hat what we will be having will get cancelled out. So, mu will be replaced by mu hat, and that is equal to x bar. So, this would be a null vector. So, there will not be any contribution coming from here. So, we will have the exponent to be given by minus n minus 1 by 2 trace of sigma inverse s. Now, let us write this term as 2 pi to the power minus n by 2 for convenience. We write it in the new notation as minus half trace of sigma inverse a matrix A, say. What is that matrix A? Where this A is equal to n minus 1 times this S matrix. So, that is nothing but that particular product I equal to 1 to n x I minus x bar into its transpose, right. So, this is now the form of the likelihood which we denote by, say, star 2. This is the star 2 form of the likelihood at mu equal to x bar, the maximized likelihood point. Now, maximization of star 2 is equivalent to maximization of log of this likelihood. Maximization of star 2 is equivalent to maximization of log of star 2 natural logarithm, that is of minus np by 2 log of 2 pi, then we take sigma inverse. So, we will take this as positive sign n by 2 log of determinant of sigma inverse. So, what we have done is we have kept this sigma inverse and taken the positive sign n by 2 and taken the log of that. So, it is plus n by 2 log of determinant of sigma inverse, this minus half trace of sigma inverse A, right. Now, note that this particular quantity is constant, and hence there is nothing to maximize here. So, that is of n by 2 log determinant of sigma inverse minus half trace of this sigma inverse A, right. Now, we will do a bit of adjustment here, that is of n by 2 log determinant of sigma inverse A. So, what we have done is we have introduced an A in order to have a similar expression as to that what we have here on the trace, so A is a matrix which does not depend on sigma, so that is not going to matter much. So, this is the second term, which is minus half trace of sigma inverse A. So, this is minus half trace of sigma inverse A. Then we have actually taken this A matrix here, so we will have to make adjustment for that. So, determinant of this matrix would be determinant of this plus determinant of this into determinant of A. So, that we will require a term which is n by 2 minus log of determinant of A in order to adjust that particular term. Now, once again see that this particular term is independent of sigma, and if we are interested in finding the sigma which would maximize the likelihood star 2, that is not going to depend on this particular function, because this is independent of sigma. That is of n by 2 log determinant of sigma inverse A minus half trace of sigma inverse A, right. So, in order to find out thus the maximum likelihood estimator of sigma, we can maximize this particular quantity what we have here with respect to sigma, and that would lead us to the maximum likelihood estimator. Now, let us denote by lambda j. Let lambda j denote the eigen values of this matrix sigma inverse A, of this sigma inverse A. Now, this j, of course, what is the dimension of this sigma inverse A? Sigma was coming from the p dimensional multivariate normal distribution. So, that is p by p, and A is a constant multiplier of the sample variance covariance matrix, that is also a p by p matrix, and hence the order is p by p. Sigma is positive definite, and with probability 1 A will also be positive definite, and hence this matrix entirely is positive definite, and thus this j is from 1 to up to p, right. So, suppose lambda j denote the eigenvalue of sigma inverse A. You may also note the following, that this, since lambda j's are the eigenvalues of sigma inverse A, lambda j is also the eigenvalues of A half sigma inverse A half matrix. That is easy to see, because if you look at the eigenvalue equation, then this would lead us to this, right. Now, we will replace this, let us denote this by star 3. So, this is that equation. Now, if lambda j's are the eigenvalues j equal to 1 to p of the sigma inverse A matrix, then this star 3 is equal to n by 2 log of, now determinant of this particular matrix would be product of the respective eigenvalues. So, its product j equal to 1 to n, this lambda, I am sorry, this is for j equal to 1 to up to p, this minus half. Now, trace of sigma inverse A would be just sum of these eigenvalues. So, this is lambda j. So, this is equal to n by 2. Now, log of this product is a summation of this log of lambda j terms, this minus half summation lambda j. So, this we can write, this, these summations are j equal to 1 to up to p, j equal to 1 to up to p. So, this is equal to half summation j equal to 1 to p n times log lambda j, this minus. So, we have taken this half outside there. So, what remains is this lambda j, right. So, in order to maximize the likelihood, we can maximize this particular quantity with respect to what now? With respect to these lambda j quantities. And what is that lambda j which should maximize this likelihood? If each of these lambda j's are equal to n. So, this is, so star 4 is maximized if lambda j is equal to n for all j equal to 1 to up to p, right. So, that is basically the lambda j. Now, lambda j actually is a crucial term. Lambda j is what is now being involved, which is being associated with this unknown covariance matrix sigma, and that lambda j being equal to 9, that lambda j being equal to n for j equal to 1 to p is what is going to give us, lead us to rather the maximum likelihood estimator. So, this would imply if all lambda j's are equal to 1, lambda j is equal to n, then this would imply that this a half sigma inverse a half that is equal to p, I will say what these terms are, d lambda n times I p, p prime, where p is now holding the orthonormalized eigenvectors corresponding to this particular matrix. So, this is what the factorization what we have. Now, these are orthogonal matrices. So, what we have that is n times I p. Now, using this particular result, it is simple to get to the maximum likelihood estimators. So, we have this particular expression if the eigenvalues, the maximizing eigenvalues are all n, then this a half sigma inverse a half, which we had actually seen here that lambda j's are also eigenvalues of this a half sigma inverse a half matrix, and hence this in terms of its spectral decomposition we will have this p d lambda, which is this matrix now p prime, and that is equal to n times I p. That is sigma inverse is going to be equal to, now this is a half. So, pre and post multiplying by a minus half, what we will be having here is a inverse term here, and thus this would imply that this sigma is going to be 1 upon n a matrix would maximize the likelihood function with respect to this sigma matrix. And what is that? So, this would imply further that this sigma hat maximum likelihood estimator is going to be 1 upon n a, and if you remember what a is that cross product matrix. So, that is x I minus x bar, x I minus this x bar transpose I equal to 1 to n. So, this thus is the maximum likelihood estimator, which in our previous notation is nothing but this S n. So, it is the sample variance covariance matrix with a divisor n is thus the maximum likelihood estimator. So, thus we have proved the following, that x bar vector is the maximum likelihood estimator of this mu vector, and S n, this matrix with the sample variance covariance matrix with a divisor n, is the maximum likelihood estimator of the sigma matrix, right. So, these two, thus x bar vector and S n are the two maximum likelihood estimators. Now, this also reminds us about the univariate normal maximum likelihood estimator, where x bar was also the maximum likelihood estimator and the sample variance with a divisor n was the maximum likelihood estimator of the sigma square quantity corresponding to an univariate normal distribution. It is just to be noted that this x bar, as we had seen earlier, is an unbiased estimator of mu. On the other hand, S n is not an unbiased estimator of the sigma variance covariance matrix. However, it is going to be unbiased in the limit. In the next lecture, we will try to derive the distributions of these maximum likelihood estimators x bar S n or S n minus 1.